Alrighty. Well, thanks everyone for coming. Yeah, so as I was sitting down to talk through, think through what to talk about today, there's just like a lot of stuff that we can kind of skip just because it's, stuff Pangeo has been doing for years. So not going to talk about analysis ready cloud optimized data. Not going to talk about cloud native geospatial or scalable Jupyter hubs. That's kind of like Pangeo's bread and butter, been doing it for years. And these are things that the Planetary computer has taken, stolen, built upon, and continuing to iterate on. So that's stuff that we're very appreciative to the Pangeo community for trailblazing. So instead, we'll be focusing on things that we're doing on the Planetary computer that might be useful for Pangeo, mostly focusing around how we're using STAC for cataloging data, and then various APIs, many built on top of that STAC metadata that support geospatial data analysis. Okay, so first of all, it's probably worth mentioning, like, why is someone from Microsoft here at all? So my team is under Microsoft's environmental sustainability group. And this kind of came out of a recognition that climate change, changing environment is important to the company. So there's like risks associated with climate change, concrete things like what's the probability of this data center flooding? How is that changing with the various climate change scenarios? But it's also important to just like the company itself, because it's like taking care of the climate's the right thing to do. And it's important to our customers. So they're facing similar risks and decisions around how to address climate change. So that kind of motivated the formation of this team. And last year, a couple of years ago, Microsoft made a bunch of commitments around things like being carbon negative, water positive, zero waste, and then protecting ecosystems. So that's where the Planetary computer falls. So there's some kind of obvious protecting ecosystems, like protecting land, setting it aside. But then there's this Planetary computer thing, which kind of is an acknowledgement that many environmental sustainability challenges look a lot like geospatial data analysis problems. And so that's where the Planetary computer comes in. It's this kind of nice name for a few different things. So first of all, it's a bunch of data in Azure. So Pangeo community is pretty familiar with the benefits of these very scalable file systems for accessing data in cloud optimized format. So a bunch of data, mostly coming from public sector data sets that's available in blob storage. That's like a lot of work. It's nice to have, but we do feel like it's important to have higher level APIs to facilitate data analysis built on top of that. So that's where STAC and our APIs come in. There's the hub, which you all know the benefits of, but it's really nice to have this convenient place. Just log in, start to do your analysis on that data from compute that's physically close to the data. So you can use the Planetary computer data from anywhere. It doesn't have to be from the hub, but that's one way to do it. And then finally, recognizing that all this is in support of environmental sustainability decision-making. It's not just data analysis for its own sake. So that's where these applications come in. So building on top of the data and the APIs, putting whatever research is done in the hub to use for environmental decision-making. All right, speaking about the actual data, again, it's all in blob storage, excuse me, in cloud optimized formats for the most part. That's going to mean COG for raster data, so cloud optimized geotiff for raster remote sensing data, ZAR for Earth systems data, and then Parquet for tabular data. So we'll see examples of those in just a second. That is mostly in private blob storage containers. And then we have an API for getting read-only SAS tokens, is what blob storage calls them, shared access signature. So you append that token to your URL. And then you can open it up in any system. At that point, it's just a regular URL to a cloud optimized geotiff or whatever you're working with. The actual processing, so there's a lot that goes on, a lot of different systems that come together. For the This is mostly like the raster side of things. So like Landsat, Sentinel, kind of starts out with the open source packages in STAC tools. So this tells how to take like a set of cogs and turn the generate STAC metadata for them. That gets combined with this ETL workflow thing that's currently closed source. Will probably eventually be open source, but it needs a rewrite first. So that's happening all in Azure DevOps, but really it's just kicking off big Azure batch jobs. So take all these items and blob storage, or fetch them from USGS or whoever our partner is. Do the cloud optimized conversion if necessary using tools like GDAL, and then using STAC tools to generate the STAC metadata. So that generates two artifacts. The data goes into blob storage, the cloud optimized data, and then the STAC items get ingested into a database. This is one way data gets to blob storage. The other way is through Pangeo Forge. So we're using that for some of our Earth systems data sets. I believe Terra Climate went through Pangeo Forge. And then we have some additional ones coming online soon. So like I mentioned, the data goes to blob storage. The STAC items, so these are just JSON documents, one for each scene. It's kind of exactly what a scene is varies from like mission to mission, but in the case of like Sentinel, it's a snapshot at some date time at some spot on the Earth with a whole bunch of bands, a single cog for each band. So that item gets ingested into a Postgres database that kind of powers the STAC APIs. So the database also has PostGIS for spatial search. So when you're doing spatial queries, we're using PostGIS for that. And then pgstack is this open source library for kind of teaching Postgres to understand STAC items and STAC queries, things like that. So the final layer here, closest to the user, is the APIs. So there's a STAC API, which we'll see an example of in just a second, but this is a web server. It's using STAC Fast API, web application. You make requests to it, it talks to the database, gets the data, and sends it back to you. Again, this is just on the kind of metadata side, the searching side. When you're actually fetching the data, that's coming straight from blob storage. So there's no bottleneck in the middle. You get all the scalability of blob storage. And then we have a tile server and various data APIs, which I'll show you. But again, these are trying to help out with the data analysis side of things. Okay, so for the actual demo, we're just going to they'll be pretty boring demos, but we're just gonna see how we can access various types of data. So again, we're using PyStack for the catalog, and we use PyStack client to do the requests, but these could be HTTP requests if you wanted. In this case, we will search for all of the items covering this area of interest from Sentinel-2 over this date time. And we'll also throw in this query for only give me items that are less than 10% cloudy. Okay, so there's like 20, 30 million Sentinel items in the database, and it's able to quickly filter all of those items down to just the few that we care about that meet our conditions. It's worth reflecting, like this is like the original use case for STAC. So it's good that it does a good job at this. When you're dealing with a bunch of files and blob storage, it doesn't have the same structure as something like ZAR. So it's nice to have this API on top that can get from all of the universe of Sentinel items that are out there to just the ones you care about. These items, they're actually like GeoJSON features. So you can load them up into GeoPandas. This is just an excuse to play out with the new GeoPandas Explorer method. So we have our area of interest in yellow there, and then all of our items. So there's some that cover the whole thing. There's some that just clip it here. Okay. And then we're over somewhere in Alaska. We'll filter them down using to select just the least cloudy item. So again, using that cloud cover extension, this is some metadata about the data that's been captured in STAC. Here's the data API. This is, again, just making a REST API call. It's taking all of the URLs that are in this item and then appending that read-only SAS token. So you can do this anonymously to publicly access the data. This is just some way to kind of keep an eye on what data is being used, mainly so that we can, if someone is like extracting all of Sentinel out of West Europe, that's going to cost us a lot of money. So we need to be able to clamp that down if necessary. Okay, and then finally we have STAC. This is again a nice way. These stack items are kind of describing where the values are actually at on Earth and in time, and in this case in this band dimension. So we're able to quickly go from this metadata to an X-ray data array, and very importantly, we didn't have to open any files. So that this is actually extremely fast. We're just doing it based on metadata. And then when we go to actually compute, we'll be making the reads from the cloud optimized geotiffs. Okay, so that's our systems data, or sorry, that's raster data, remote sensing data. For Earth systems data, we're mostly storing that in ZAR. It's worth mentioning that we're able to generate these kind of nice summary detail pages for each of our data sets. So we have text descriptions, various extents, temporal and spatial extents. And then for data sets that come from ZAR, we can use the DataCube stack extension to indicate what's various important information about the data set, like the dimensions, like the variables. So this is just coming from some JSON here, and then the front end knows how to pick out the important things for that data set. So we have all the variables here. And again, this came from the ZAR metadata. Okay. So we're again going to use STAC to kind of make the data analysis, data access a bit easier. So we'll read in the stack collection, the JSON object I was just showing you with PyStack. And then we'll access the ZAR. We have links to both the HTTPS version of the dataset and the ABFS, the Azure blob file system version. They're both pointing towards blob storage, just using different protocols. Again, the URL here is the path to the root of the ZAR store. The nice thing about these stack metadata is we can include additional things like you should be opening this file with consolidated equal true. So we'll go ahead and open up that asset using fspec xarray. And again, the only thing we needed to know here is the key for the collection and the key for the asset that we want to use. Everything else, like if there were any keyword arguments here for this mapper, like you would if you were using the blob storage route, you could pass those here, and that'll all be contained in the stack metadata. Second thing to note is that stack is flexible enough that you can extend it. So the core stack doesn't need to know anything about ZAR or xarray, but it can be extended to support those use cases. Last one, tabular data. So these are mostly stored in Parquet, actually exclusively in Parquet. So for this example, we'll grab some Parquet data sets that we did for the Census 2020. So we have stack items. Each one of these represents a table. So we have like the population for each census block, the geometry for each census block, and then various aggregations like the county level, school districts, congressional districts, all those various aggregations that the Census Bureau produces. We can go ahead and read those in. Again, we're using stack extensions here to say, what are the additional storage options that you need? In this case, it's like the account name, the credential, which I probably shouldn't share, but it'll expire soon, so it doesn't matter. So there's the storage options for that data set. That's geometry, and then we can load in population as well, and then do our analysis from there. So again, that's the last one was tabular data. Again, all three of these types of data, we're using Stack to facilitate data access. Last thing, my time's almost up, but gonna look at some of the data APIs. So if we look at, say, a Landsat item, we have this this asset that actually points back to planetarycomputer.microsoft.com/API/data/items. And so this is a tile server, an XYZ tile server, I think it's called, that it's like common in geospatial stuff. So like other systems like Leaflet know how to deal with these tile JSON things. So we can pass that URL to Leaflet and it knows how to render this stack item. And on the back end, that data API is connected to a T-tiler deployment, which knows how to like do really cool things with mosaicing stuff. So we can like zoom in on the Mississippi River Delta here, select a data set like Sentinel, and T-tiler will automatically query our stack catalog for items that meet some conditions like low cloud or some date time conditions, and then dynamically mosaic them together, apply various band combinations to convert the data from those bands into some sort of image here that you can pan and scroll around. And then if you want, we have little code generation snippets, so you can copy the CQL is the query language here that Stack is using. Copy it and then launch into your hub for your analysis. So you can start your analysis here in the Explorer and then run with it using all the tools that we know and love. Okay, that is, I think I'm at time now. So a few things coming up, user data support. So right now, this kind of tool chain works well when you have stack items, which we've generated. But what if you have your own data sets? We want to support that. Event-driven ETL, like faster, have the stack items and COG show up faster in our API, forecast data. Yeah, so that's it for me. Sorry, I ran a little long, but hopefully we have some time for questions now.